Hello, everyone. A very good morning to all of you. So today we are going to talk about different types of equation solving techniques. So in previous meetings, we have already talked about how to solve a linear equation and a quadratic equation and a rational equation, which is ultimately reducible to a linear equation. So today we are going to talk about slightly different types of equations. You will see what they are. And since they are different, so each one of them will be having a different approach or technique to solve. So without a delay, let's get started. So I'm going to share my screen here, and this is the PowerPoint open here. So just let me do this setting, duplicate slideshow. And here we are. So these are the type of equations we will be looking at. Firstly, we'll talk about equations with rational exponent. So you will understand the meaning of rational exponent once I introduce those kind of equations. And then we will have a look at polynomials of degree greater than 2. As I said, when degree is equals to 1, this means we have a linear equation. So we have already seen how to solve that. And we have also seen how to solve degree 2 equations, which we specifically call quadratic equations. And then this will be followed by radical equations. So clear from the name that here we'll see radicals into the equations. And then finally, we'll talk about absolute value equations. So the absolute value means introducing the modulus or absolute value of expressions. So there could be x sitting inside the modulus, or there could be a linear factor sitting inside the modulus, and so and so. So now let's go through each one of them one by one. All right, so let's first understand how to solve equations with rational exponent. So as you can see, this is the equation which is given to us, and look at the unknown variable x. The unknown is with the power 3 over 2. So clearly this is not a polynomial equation, because in polynomials we can only see terms like x, x squared, x cubed, x raised to power 4. So the powers of x are positive integers. But here, since we see an exponent 3 over 2, which turns out to be a rational number, so therefore we say x is sitting there with a rational exponent. So the goal is still the same. We have to find the value of x. So let's see now how to do that. So in order to isolate x on left-hand side of the equation, what we will do, we will take the reciprocal of the existing rational exponent. Now, what is the reciprocal of 3 over 2? The reciprocal of 3 over 2 is 2 over 3. The moment you raise it to the power 2 over 3, so obviously you have to do that on both sides of the equation, because you can't change the equation. So whatever algebraic operation you are doing on one side of the equation, it has to be done on the other side as well. So that would result into 125 raised to power 2 over 3 on the right hand side as well. So now what's the benefit of doing so? So now you will see on left hand side, I'm only left with x raised to power 1. Because if you remember the rules of exponent, so we know that a raised to power m raised to power n is equivalent to a raised to power m times n. So if I have x raised to power 3 over 2 and then 2 over 3, so eventually they get multiplied and I get x raised to power 1, because any number multiplied by its reciprocal results into 1. So x raised to power 1 is equal to 125 raised to power 2 over 3. And x raised to power 1 means x. So you got the solution. So now you understand why we choose the reciprocal of the existing rational exponent for the new power, because we wanted to get x raised to power 1. And that's it. This is the final solution. Now, depending upon what the resulting number you're getting, you can obviously simplify it. So I can simplify this. So what is 125 raised to power 1 over 3, and then it will be squared. So I'm simplifying this in a way that first I'm processing the rational power, and then I'm going to process the integer power, the numerator power. So what is the cube root of 25? Which is 5, and then square of that. So the final answer is 25. So x equals to 25 is the final answer of the given equation. So I hope you understand these steps and you will be able to replicate it given any equation of this kind. So that is the idea, how to solve equation with rational exponent. Let's do one more example, which is slightly different than the example which we just finished. This is also an equation with rational exponents for the variable x, but as you can see, there are two terms containing x and their exponents are also different. So how to solve this kind of equations? So what we will do, we will move all the terms containing x, regardless of whatever their exponents are, on one side. And we know that ideal way to do it is shift everything, shift the variable on the left-hand side of the equation and the constants on the other side. So when you move x raised to power 1/2 on left-hand side, so obviously you need to subtract it, and the right-hand side you get 0. Now here we have to do factorization because I have to have some power of x coming out from both of these terms, and then I will be left with some resultant powers. Now, how do you know, or how do you know what power will come out as a factor and what will be remaining inside? So I'll give you example in integers, and then you will be able to understand that. So for example, if you have an expression like x squared minus x equals to 0. So we know that x raised to power 1 is the smallest power of them. So you can factor out x, resulting into x minus 1 inside the parentheses. How do you get that? How do you get this x raised to power 1? Because from x raised to power 2, if you already take x raised to power 1 outside, you compute this resultant power by subtracting 1 from this. So 2 minus 1 equals to 1. That's why I'm left with 1 here. We can take another example. Say you have x raised to power 4 minus 3x equals to 0. So if I take x outside, here I'll be left with x raised to power 3 because it is 4 minus 1. 1 goes outside, so 3 is left inside. And then here x has already gone outside, so nothing left, so just the constant. So that's how we do factorization in polynomials containing integer powers. So similar technique is going to work here. The only difficulty we sometimes can face that sometimes it's not easy for us to identify which one of them is the smaller power. So have a look at the magnitude of those numbers. So 3 over 4, 1 over 2. Now 1 over 2 can be equivalently written as 2 over 4. So out of 3 over 4 and 2 over 4, we know that 2 over 4 is smaller. So that's what is going outside. And once you do that, so see what you are left with inside, 3. And here, the resultant power will be 3 over 4 minus 2 over 4 because you took 2 over 4 outside, so you will subtract it from this power. And this was already x raised to power 1 over 2, which is same as x raised to power 2 over 4. So the entire x raised to power 2 over 4 is outside. So you are left with just 1 here. So that's what you are left with. Now you can do the subtraction of powers in the subtraction of fractions in the power. So 3 minus 2 will be 1 over 4 minus 1 equals to 0. So now this expression which you have just obtained is the factorized form of the original given equation. And once we know we have the factorized form, we can use the zero product property. The zero product property tells you that each of the factors can be put equals to 0 individually to work on two different equations individually. So we have isolated the given rational exponent equation into two different factors which contain only one exponent term. So originally this had two different exponents, but now we have got two separate equations with only one x raised to power a unique exponent. So what's the solution of this? Clearly, x equals to 0 because x raised to power anything positive is 0 will always result into x equals to 0, because there is no other number which when multiplied with itself or raised to power anything can give me 0 here. So this is surely x equals to 0. The solution coming from this factor. From the other factor, let's see what do we get. 3x raised to power 1 over 4 equals to 1. So I first add 1 on both sides, and now you divide with 3. So when you divide with 3, you will get 1 over 3. Now this is similar to example number 1. What was the situation in example number 1? You have x raised to power something equals to a number. So how did we solve it? By taking the reciprocal of the exponent which was originally present. So now look at the exponent 1 over 4. What is the reciprocal of that? Reciprocal of 1 over 4 is 4. So I have to raise to the power of 4 on both sides. So once you do that, on left hand side, you'll just get x. On right hand side, you'll get a power of 4. So 1 over 3 raised to power 4 is 1 over 81. So finally, okay, so this was just a rough work, like nothing to do with this problem. So the final answer is x equals to 0 and x equals to 1 over 81. These are the two solutions of the given equation. So this is another type of equation with rational exponent. So obviously the technique is a little bit detailed, longer, but if you're clear with the concept of factorization and zero product property, should be able to do that. Right? So practice more questions like this towards the end of the chapter. Now let's have a look at another type of equation. It's a polynomial, but of degree greater than 2. So polynomial equations with factoring. So now, again, let me give you a general statement. We are not looking at all the possible equations of degree greater than 2. We will be working on only some specific types of polynomials of degrees greater than 2, because not every equations of degree greater than 2 can be solved with these techniques, which I'm going to demonstrate. But we just want to learn these two techniques. So we'll be working on a restricted class of examples. So the kind of examples I introduce here will be the kind of examples you will find in the chapter. So they will be helpful. Okay, so let's solve this polynomial through factorization. It's similar to what we just did in the equation with rational exponent. So let's see what we get. So 5x raised to power 4 is 80 times x squared. So let's first subtract 80 times x squared from both sides, getting a 0 on the right hand side. And now factor. How will you factor? So from 5 and 80, the coefficient, I can factor out 5 because I know 5 times 16 is 80, right? So 5 divides 80, so I can factor out that as well. And from x raised to power 4 and x raised to power 2, I will factor out the smaller power, which is x squared. And then I will be left with x squared because 5 is gone outside, so no coefficient. From x raised to power 4, x squared is outside, so I'm left with resultant power of 2. 4 minus 2 is 2. Minus 80 gives me 16. And then x squared is outside already. So that's the thing which you are left with. And now you can use the zero product property, putting each individual factor equals to 0. So when you put 5x squared equals to 0, so you divide with 5, you will get x squared equals to 0. And the only solution you will get from here is 0. So this is a quadratic equation. So ideally, we are supposed to get two solutions in general from a quadratic equation. But this being a specific type, I'm getting only one solution from here. So x equals to 0 is the solution coming from this factor. And this is again a quadratic equation being a second degree. And I know I can use the square root technique here to solve this because there is no x term present. So we know when there is no x term present, we can always use the square root taking technique. So x will be plus minus square root of 16. And what is square root of 16? 4. So I got two solutions from here, plus 4 and minus 4. So in together, I got three solutions, 0, 4, and -4. So these are the solutions of the given equation, which we found through factoring. So we did not have to learn any explicit way of solving a fourth degree equation, but eventually what we just did was using our knowledge of factorization and zero product property and how to solve quadratic equation. So all those combined together is giving me a set of solutions for this equation. Now let's take another example. Here we have an example where we cannot solve it with factoring because a non-zero constant is there. If you compare it with the previous example, we were able to factor out a power of x only because there was no constant present here, right? But in this equation, it's a cubic equation, as you can see, degree 3, but there is a constant sitting here, so we cannot do it with the factorization technique. So there has to be a different way to solve it. So that's what we call grouping. So let's try how we can use grouping to solve this equation. X cubed plus x squared minus 9x minus 9 equals to 0. So you combine the terms in pairs and then figure out what can be taken out. Now from x cubed plus x squared, what factor can be taken out? X squared. And then we are left with x plus 1. And then from minus 9x minus 9, we can factor out, first of all, minus because both of the terms are negative. So I can take negative outside. I can take 9 outside because 9 is present in both of them. But I cannot take any power of x as a common factor because there is no x here in the constant term. So nothing else than that. X plus 1 equals to 0. So now you look at this expression and this expression. So x plus 1 is sitting as a common factor, right? In both of them. So take out that. And then you're left with x squared minus 9, right? X squared minus 9 after taking x plus 1 outside. So you see, it's not, we were not able to factor it, but we were able to factor it with a different technique with grouping. So now you can use the zero product property to put individual factors equals to 0. Now, since the original equation was a cubic polynomial, so it is factored into a linear and a quadratic equation. It's easy to solve this equation. X equals to -1 is the solution. And again, similar type, take the square root. So you will get plus minus 3. So I get 3 solutions, -1, -3, and +3. So these are the 3 solutions of the original equation. Now, if you want to do verification of your solutions, we know how to do that. You can take them one by one, substitute into the equations, and see which ones are correct. And if they are wrong, so that means you have to check your calculation. So that's about specific type of polynomial equations of degree greater than 2. We're demonstrating 2 techniques here, factoring and grouping. And now let's have a look at the third type of equations we want to talk about today, which is a radical equation. So I know you are familiar with the meaning of a radical. So radical means this symbol. So in general, a radical equation, you could also have a radicand containing 3 here, which we know this means is raised to power 1/3. But when you have nothing here, so this is equivalent to raised to power 1/2, which is square root of that. So basically, this is actually also an equation with a rational exponent, because you are seeing it in a radical form does not make it any different from the rational exponent equation, because that radical is equivalent to the rational exponent 1/2 or 1/3, depending upon what it contains. However, when specifically that rational exponent is a square root, so we have a different way to solve that. We can solve it using the existing techniques, using the known technique, which we demonstrated with the first type. However, as I said, when this is a square root, so this makes that equation unique. So we have altogether different way of solving it. So that's the definition of radical equation, an equation containing terms with a variable in the radicand. That means there should be a variable here, something about x happening here inside the radical. Only then you say this is a radical equation. If it is an equation like, say, x squared plus square root 5, x equals to 0. This is not a radical equation. Why this is not a radical equation? Because although it contains a radical, But look at what is there inside the radical, just a number. We can solve it by the ordinary techniques which we already know for quadratic equations, right? It's a quadratic equation, not a radical equation. So for an equation to be a radical equation, there has to be a variable sitting inside the radical sign. So let's have a look at these type of equations. Now, even in this category, we have two further categories of questions. The first one is equations with one radical. Now here I have outlined the steps to solve radical equations, but I'm going to demonstrate the same steps with example. So it would be better for you if you first go through the example and then we'll come back to read these steps. So that's the first kind we are going to look at, and we call this kind the easiest kind of radical equation, where you have only one radical present, and other than that, you could have a combination of variables and constants and other things. So let's have a look at this equation. Solve square root of 15 minus 2x equals to x. So now think about the process. I just demonstrated in the examples which we just finished that suppose you have an equation like this. See, the ultimate aim is still the same. We want to find x. So when x square is present, and if you want to get x, what we do? We take the square root, right? And now we are into an opposite situation. X is sitting inside a square root. I want to get x. So instead of taking the square root, because the square root is already taken, I have to now square it. So when x square is given, to get x, we take the square root. When square root is given, to get x, we square the equation. So that's the step you have to do, squaring both sides. And you can't square only on one side. You have to do whatever algebraic step you are applying, you have to do it on both sides of the equation. Squaring both sides, I will get square root of 15 minus 2x square equals to x squared. Now, what's the benefit of doing this? So on left-hand side, I'll be just getting 15 minus 2x, because we know that square root of x square is simply just x. So whatever is sitting inside the radical, you just copy and paste there. So 15 minus 2x will be now free from radical. So this is the process of making that algebraic expression free from radical. You just do the square. So that also introduce a square on the other side. So whatever is there on the right-hand side, be it a number, be it a variable, be it an expression containing a combination of number and variable, whatever is it, you have to introduce the square. And I'll look at this equation. And if I move x squared on this side, so I have to subtract x squared. And then just writing that simply, taking out minus common, I get this equation. Now, what type of equation is it? Quadratic equation. We are already familiar with it. So now, since you already know there are various techniques of solving a quadratic equation, you can do factorization, you can do quadratic formula, you can do completion of squares, and so and so. Now here, since I can see the factors quite easily, so I'm going to adopt the factorization. But again, there is no restriction. If you're not able to see the factors, you can directly go for the quadratic formula, the discriminant formula, which we are familiar with. So after factorization, I'll get, so the factors of negative 15 are 5 and minus 3, because 5 and minus 3 will give me 2 in the middle. So it's x plus 5, x minus 3 equals to 0. And then putting individually both of the factors equals to 0 will give me x equals to negative 5 and x equals to 3. So these are the two solutions which I obtained using this technique. So now there is something which we need to be careful with, which is known as extraneous roots. Now, before that, whatever kind of equations we have introduced or solved, I was always telling you that when you get the solutions, you can do the verification by substituting them back into the original equation. But that step was like optional. It was just to convince you whether your calculations are right or not. But in this kind of equation, the radical equations, whenever you get solutions, you have to do this step. You have to do the verification. You'll understand the reason now when I do that. So let's test both of them one by one and see whether both are actually the real solutions or one of them is not the solution. So the one solution which is there, like you see it here, but that's not the actual solution of the original equation. Those kind of roots are known as extraneous roots. So these roots or these solutions just appear as a part of solution, but fail to satisfy the original equation, right? So the roots which are there, they are there because you adopted a certain strategy to solve that equation, but actually they are not supposed to be there. So how will I be identifying these roots? By substituting them back into the original equation. So let's first do the testing. So let's first test x equals to 3. Now there is no order, you can do testing in any part. So let's first test x equals to 3. So original equation is square root 15 minus 2x equals to x. So when I'm putting 3 in place for x, that's how you do the testing. Replace x with 3 in the entire equation. Now 15 minus 6 is 9, so square root of 9 is 3. Perfect. So this actually satisfies the equation. So x equals to 3 is actually a true solution. Now let's test the other one, x equals to -5. So take the original equation, put -5 in place for x. Now, even before simplification, I know this is incorrect because you are putting square root equals to -5. So it doesn't matter whatever is there inside the square root. A square root can never be equal to a negative number. So here also I can just conclude this is incorrect. If you want, you can do the simplification. So 15 plus 10 will give me 25. So square root of 25 is -5. This is mathematically incorrect. So that's why this solution I'm going to call extraneous root or extraneous solution, but the other one is the true solution. So this is now an important step. You cannot just skip this step. You have to do it in radical equations. So that's end of the solution for this question. Now let's do another example, which also contains one radical. So we are going to follow exactly the same steps. So square root x plus 3 is 3x minus 1. So squaring both sides, I'll get just x plus 3 on left-hand side, but on right-hand side, I have to do the squaring. So many times I've seen people do it wrong here. They just do the individual square. Like if you do x plus 3 is 3x square minus 1 square. So this is incorrect. That's not how you square on the other side. You have to take the whole square of the term sitting on the other side. Now, how do you expand this? So you can write it as product of two factors and then use the maybe FOIL method to do the multiplication and simplify it. Or you can directly use the formula, which is a minus b square, because this expression looks like to me a minus b whole square equals to a square plus b square minus 2ab. So the moment you use that, so a is 3x, b is 1, minus 2, 3x times 1. So this is 9x squared plus 1 minus 6x. So when you're squaring 3x, make sure you're also squaring 3. So it's 9x squared plus 1 minus 6x. Left-hand side, you still have x plus 3. And now move everything to the left-hand side and see what you get. So minus 9x squared minus 1 plus 6x. So when you shift all the terms on the other side, their signs are going to change. What we get, minus 9x squared. Now x plus 6x gives you 7x, and 3 minus 1 gives me 2 equals to 0. And now if I just get rid of this, 9x squared minus 7x minus 2 equals to 0. So that's the equation which I am left with. And now let's see whether I have some factors here or not. So 9 times 2 is 18. And the factors of 18 are 9 and 2. And yeah, so I can write this 7 as minus 9x plus 2x. So again, you have an option because this is a quadratic equation. You can use quadratic formula or completing squares. If you're not able to see the factors, I was able to see it, so I'm using it. So I'm writing minus 7 as minus 9 plus 2, and now grouping using the technique of grouping. So 9x, x minus 1 plus 2, x minus 1 equals to 0. So this gives me x minus 1, 9x plus 2 equals to 0, and putting the individual factor equals to 0, I get x equals to 1, x equals to negative 2 over 9. So these are the two solutions which I got. And now we will do the verification part. So let's first verify x equals to 1. So when you plug in x equals to 1 in the original equation, I'll get square root of 1 plus 3. 3 times 1 minus 1. So square root of 4 equals to 3 minus 1. So square root of 4 is 2, which is correct. Hence, I would say this is the true solution. And let's verify the other one, which is minus 2 over 9. So square root of minus 2 over 9 plus 3 is 3 times negative 2 over 9 minus 1. So I can clearly see the right-hand side is negative. Even before simplifying, whatever I get after adding these fractions, we know both of the terms are negative. So this is a negative thing. Left-hand side is a square root. So square root can never be equal to negative thing. So hence, I would say this is a false solution, or the technical word for that is extraneous solution. So that's how you end up getting equations like this. So these were the examples of equations with one radical. Now we are going to move on to equations with two radicals. So they are slightly lengthier than what we just did, but the steps are similar. Now, how to deal two radicals? So do not do directly the step of squaring both sides. So whenever your equations have two radicals, make sure you have one radical on one side of the equation and the other radical on other side of the equation. So you convert that equation, you rewrite that equation in a way that you have the radicals sitting on opposite sides of the equation. So square root 2x plus 3 is 4 minus square root x minus 2. And now you do the squaring. So that would give me 2x plus 3 equals to, now this side is a little complicated. You have to do square of this. So left hand side is fine, 2x plus 3. But here, use the same formula which we used in the previous example, a minus b whole square, right? So a square plus b square. So b is also radical. A square plus b square minus 2 times a times b. So 4 square is 16. Now it's already square root, and when you're squaring it, you will be free from radical, right? So square root of x minus 2 square, the square and square root will balance each other. You will get x minus 2 minus 8 times square root x minus 2. This side you have 2x plus 3. Now move all these terms to the other side. So 2x plus 3 minus 16 minus x plus 2 equals to minus 8 square root x minus 2. Now first you simplify the left hand side. So 2x minus x giving me x, and then 3 plus 2, 5 minus 16 giving me minus 11. Now you see what's the difference between this type and the previous type. The previous type, once you do this squaring, you were completely free from radical and you just got a quadratic equation, and we already know how to solve a quadratic equation, and then the verification. But here, because there were two radicals present, so squaring them one time will not get you completely radical free. You are free from radical on the left-hand side of the equation, but not on the right-hand side. As you can see, there is still a radical present here, square root x minus 2. So I have to do squaring one more time. So once you do that squaring, you'll get x minus 11 squared equals to minus 8 square root x minus 2 square. Now you use the same formula to expand the term on the left-hand side. X squared plus 121, that's the square of 11, minus 2 times 11, 22x. 8 square is 64. See, minus square is just plus 1, so you won't see minus now. So 8 square is 64, and x minus 2 will be there because square root of square will be just x minus 2. And now you simplify this. So x squared plus 121 minus 22x is 64x minus 128. So now you move everything on the left-hand side because now I can see an equation free from radicals. And essentially, this is a quadratic equation, x squared. Now, how much is 22 and 64? So you get here 86. And here you get 249, 121 plus 128. So that's what I got. Now you land up at the same situation. You get a quadratic equation. You can use your own technique to solve it, but I'm using factorization here. So I can see 249 is 83 times 3, and 83 and 3 will give me 86. Yeah, so minus 83 minus 3 is the answer of the factors, and then solving them individually, I will get 83 and 3. So I got two solutions, and now we have to do the verification part. So the verification part is when you first try x equals to 3, let's see what we get. 2 times 3 plus 3 plus 3 minus 2 equals to 4. So 2 times 3, 6 plus 3, 9. 3 minus 2 is 1, square root of 1. So square root of 9 is 3, square root of 1 is 1, equals to 4, which is correct. Hence, x equals to 3 is the true solution. And if we do the verification for x equals to 83, so 2 times 83 plus 3 plus 83 minus 2 equals to 4. 2 times 83 plus 3. So that's going to be a different number. And the other thing is going to be, if I simplify that for you, so 83 times 2, let me do that here, is 166 plus 3. So that's 169. And 83 minus 2 is 81. Now, square root of 169 is 13. Square root of 81 is 9. So 13 plus 9 equals to 4. So that is clearly incorrect. And hence, this one is an extra root and we need to reject it. So the only true solution of this equation is x equals to 3. So as you can see, this is little lengthier than, of course, the previous time of radical equations, because there you just had to do 1 time squaring and then you got a quadratic equation. But here you have to do 2 times squaring and then getting it here. But yes, this is the strategy you have to follow. There is no alternate way of solving these equations. You have to follow all these steps. And since this involves a lot of algebra, so you should be obviously clear with all the formulas applying correctly. And yes, so these are the two commonly used formulas because you will have to do squaring often. So these will come handy. So this one and a minus b squared. So make sure you remember these two formulas and then use it wherever they are appropriate to use. So that's the radical equations. And this is another example here. I'm leaving it here for you to practice. And now let's move on to the other type of equation. The last type of equations we are going to take up is absolute value equation. Now, it's clear from the name, these type of equations will contain a modulus, an absolute value of expression into the equation, and other thing is going to be just a combination of variable and a constant. So let's just recall the meaning of absolute value mod x. So we know that if it is already a positive number, then its absolute value is the number itself. So mod of 5 is 5. We know that. Got my pen. Mod of 3 is 3. However, if you input a negative number and then take the absolute value, you are getting the positive part of it. So eventually, what I did is I multiplied -5 with another minus to make it positive. So that's the meaning of this statement, that if an expression is negative, that means mod of x is minus x. So now whenever you have an equation of the form mod of a equals to b, so then you will be splitting it up into two equations further. I'll show you with the help of this in example. And then this is something which will be very useful. So if you see an equation like there is a linear expression inside the modulus and right hand side is a constant. If that constant is negative, so clearly this equation is having no solution because this is never possible. Just like we say, you cannot, the square of a number can never be negative. The square root of a number can never be negative. Similarly, the absolute value of any expression or any number can never be negative. So for example, if I see equation like 2x plus 1 equals to -3, the moment I see a mod equal to a negative number, I immediately conclude there is no solution. Like you don't even have to do any of these steps. You can say then and there only, no solution. And if c is 0, if the right hand side is 0, say something like this, then it has only one solution. You will see how to get that. And if the number is positive, then it will have two solutions. So let's dig into examples and see for ourselves in what case, what kind of equations we have. So solve the following absolute value equations. Now inside the modulus, you will be given a linear function, linear expression in x. Okay, now how to solve it? So this will always split up into two linear equations. 6x plus 4 mod equals to 8 means either 6x plus 4 equals to 8 or 6x plus 4 equals to -8. Now it's easy to understand why is this so. I can give you a simple example first. Say you have an equation mod x equals to 2. So we know that the only two numbers whose absolute value is equal to 2 are the number 2 and number -2. So modulus equation, the absolute value equation, will be equivalent to always two separate equations. One of them you will get by simply taking the same number 8. Another equation, you take the negative of that. So do not do anything with this quantity sitting inside the modulus. That's same as 6x plus 4, but 8 is 8 and -8. So you get these two equations. Now this is nothing but a set of linear equations, right? Two different linear equations. So solve them and you get your answers. So how to solve this? So subtract 4 first. 8 minus 4, which is 4. So x is 4 over 6. When you simplify that, 2 over 3. Let's solve the other one. So 6x equals to -8 minus 4. So 6x is -12. Divide with 6. X is -2. So these are the two solutions you got. No need to do verify. Like again, it's optional to do verification for these equations. If you want to do, you can do that. Otherwise, there is no chance you will get an extraneous root here. So you don't need to do the verification. Now let's do part B. So part B looks like mod of something equals to a negative number. So clearly this has no solution. We just discussed about it here. So whenever you have this case, that the modulus is put equals to a negative number, immediately you conclude no solution. Okay, but this is now slightly different type. Mod is there, but a number is subtracted and you have a number on the other side. So first you have to bring it into this type, that the mod is on one side and the number is entirely on the other side. So mod 3x minus 5. So to move -4 here, I have to do 6 plus 4 equals to 10. Now, since this is a positive number, so that means it has solutions. It's not a negative number. Had that been a negative number, I could conclude no solution. But since it is a positive number on the right-hand side, so we will do it exactly in the way we solved part A. So this will split up into two equations. 3x minus 5 equals to 10 and 3x minus 5 equals to negative 10, and then solve this one. So 3x is 10 plus 5, which is 15, and x will be 15 over 3, which is 5. So this is one solution. Now 3x is minus 5 now, because minus 10 plus 5 will be minus 5. So x will be minus 5 over 3 is the other solution. That's it. You got two solutions. They are the final answer. And then the last type is when the modulus is equated to 0. Now this has solutions. The mod can be 0. So we'll adopt the same technique we used in A and C, that you take whatever is sitting inside the mod, and once you take positive part of this number, and then you take the negative part of the other number. Now, since 0 is the only number for which plus 0 and minus 0 is same, right? The positive and negative is same. Plus 0 is same as minus 0. So eventually they are not two equations. You're practically solving one equation only. So that's why we say, in this case, that if the right-hand side constant is 0, so you'll get only one solution in this case. So when you solve this equation, subtract 10, divide with minus 5, you'll get 2. So x equals to 2 is the only solution of this equation. So that was all about the absolute value equations. These are the types you can get. So that's the end of the type of equations we have. So that's all for today. See you next time.